And some people really hate CCS, carbon capture and storage, and I just say get over it because we're going to need it.
As I am in this business quite a long time, I remember same people hating the sulfurization plant when I started my career back in the late 80s. Nobody was believing that we were going to retrofit all these coal plants we had at that time with desulfurization. And at the end, because it's an end-of-pipe technology and because there was a societal commitment for that, it becomes the standard state-of-the-art technology.
Hello, I'm Michael Liebreich, and this is Cleaning Up. Climate change is often characterized as an environmental problem, or a policy problem, or a finance problem. And of course, it is all those things. But it is perhaps first and foremost an engineering problem. Most emissions are caused by the stuff that we build and use in the physical environment. So it gives me enormous pleasure to note that of the organizations that we've brought into the leadership circle of Cleaning Up over the past year, they include some of the world's preeminent engineering companies. Wärtsilä, producer of the largest and best reciprocating engines in the world. Schneider Electric, extraordinary electrical engineers. Arup, the built environment. And our most recent member, I'm delighted to welcome Mitsubishi Heavy Industries. And joining me today, Emmanouil Kakaras, who is their technology evangelist. He was recently their vice president for the green transition. Please join me in welcoming Emmanouil Kakaras to Cleaning Up. Emmanouil, welcome to Cleaning Up.
Thank you very much for having me here, Michael. It's delighted to be here and enjoy the conversation with you.
And it's absolutely tremendous to have you on board the leadership circle. We're becoming quite an engineering powerhouse. What I want to do is let's start where we always start, which is if you could say who you are in your own words, you as an individual, and then we'll get on to Mitsubishi Heavy.
Thank you. So I'm an energy professional. This is how I would characterize myself. And I'm also a researcher by education and training. I'm an engineer. I have something like 30 years of experience after my PhD in energy engineering. I'm also a university professor in Athens and in different places of the world. And I am also working or advising Mitsubishi Heavy Industries in that context.
And you've got some patents, I understand.
Oh, thank you for mentioning that. In fact, that's part of the research mission of an academic guy having an engineering background. And yes, I'm quite proud of that. And that was on power to fuel. So it was a field of specialization because I was for 20 years university professor in Athens, and during that time I got myself familiarized with the energy transition business, and the power to fuel is a key pillar for that. Whether this pillar is strong enough or not, it remains to be seen in our discussion.
We're going to get into that power to X stuff. But you, just to be clear, so you, because your role is now a technology ambassador, but you have been the executive vice president for transition technology. So you must have been pretty much full time for a while with Mitsubishi.
Yes, I've done. Although I don't like to speak about myself too long, but I've done the opposite path than usual. I was very early fortunate enough to become a chair professor in Athens. And then I was fortunate enough to do a career turn some 14 years ago when I was invited to join the industry again, mainly because of my track record on energy transition. And then I went up the executive ladder. You're familiar with the term yourself. And I was managing energy transition until very recently for MHI in Europe, Middle East and Africa. And now I'm continuing my collaboration with MHI as a senior advisor on the same agenda, so to speak.
And I very much like the story which you told me just before we started filming about being plucked by, at the time it was Hitachi, before it became part of Mitsubishi,
Yes.
and being immersed in the Japanese business and technology culture.
Sure.
But let's jump to Mitsubishi Heavy, which then acquired that Hitachi business that had plucked you out of your professorship. Mitsubishi Heavy. Now, my audience will probably not know all the different bits of the different Mitsubishi group. So let's kind of peel the onion down from Mitsubishi group's got all these different bits. Which bit is Mitsubishi Heavy?
So in this corporate family of Mitsubishis, because there are many Mitsubishis, especially after the Second World War in Japan, there was a breakup of the Mitsubishi conglomerate in different pieces. Mitsubishi Heavy Industries is the machinery part of the Mitsubishi family. And the family shares the common name, Mitsubishi, and the common sign, the three diamonds, but nothing else. So Mitsubishi Heavy Industries is an technology company, an engineering company, fully independent from the rest of the Mitsubishis that you might be heard of, Mitsubishi Bank, Mitsubishi Corporation, Mitsubishi Electric, and so on and so on. So Mitsubishi Heavy Industries is a technology company, above all, engineering company, doing with different sorts of machinery and this sort of production capabilities.
It's a fascinating type of relationship organization, which we don't really have in the UK or in the US, where you have sharing the brand and very often working together, but without any corporate ownership. It's not part of a
no, it's completely independent.
Completely independent. And just to give an idea of the size of it, how many people have you got in Mitsubishi Heavy?
78,000 people.
78,000, I'm assuming a bunch in Japan, but also around the world?
Well, it's a global company. It's a global company. Of course, it has been founded in Japan. Lots of production facilities are in Japan, and we have to speak a little bit about the technology and the Japanese quality aspect on the technology and the production lines. But we are quite active all over the world, in the US, in China, and in Europe as well, with a multitude of products and services over there.
Right, and that Japanese DNA of quality and manufacturing, now of course enormously helped by the better exchange rate, because for a while Japan was enormously expensive.
No, I think of course, the financial situation and the exchange rate helps a lot, as it helps tourism in Japan as well. But it is the quality that matters.
Now, let's just, as I say, peel the onion a little bit deeper. So you've got divisions, and then we'll move on, from just complete the thumbnail of MHI, because you sit in the energy part, but that's not all of the company, is it?
Not at all. Energy is the biggest part of MHI, but we have also logistics and infrastructure. We have machinery, and we have also defense and aerospace. And the aerospace is also a kind of the crown of the jewel, the rocket launchers, the satellites, and all the stuff. Okay,
so this is really one of the absolute sort of Japanese, I would say, industrial aristocracy. I mean, it's actually one of the technology flag bearers for Japan, and I associate, or used to associate, Mitsubishi Heavy with gas turbines. So let's start there. What do you and I think that's
the best of the world, No, I think that's a very important product, but it's not. It's like a flagship product, I would say, in the sense that Mitsubishi Heavy Industries is. We claim that we have the best gas turbines in the world. Of course, there are other OEMs who will say the same, but we have several things that we have achieved very quickly, like the scaling up, like the 1700 degrees combustion temperature, the high efficiency, the high reliability, the multiple fuel use.
I've got my thermodynamics antenna is just, I don't know what antenna do, but it's ringing or doing whatever it does. 1700 degrees centigrade. And of course, higher temperatures, just for those who are not thermodynamicists, right? The higher the temperature, the higher the efficiency, or at least the higher you can achieve. You can then ruin it in other ways, but at least your Carnot efficiency is...
Carnot found it before us again.
Right, but how do you get to 1700 degrees? I mean, most metals would be melting at that point.
I think that's with special alloys and coating, to say it very simply. And of course, this goes together with a very sophisticated combustion system and combustion technology, because you achieve this high temperature, but you maintain a very low level of NOxes, which is the usual advantage of the gas turbines, which made them, in fact, in the energy generation business, the main product, the cornerstone of the energy system worldwide.
Now, we have a rule on cleaning up. We're not allowed to use acronyms. So when you say NOxes, that is nitrous oxides.
Nitrous oxides, yes.
And the problem with going to a higher temperature, you get a big benefit for efficiency, but you are likely to get...
You produce more thermal NOx. So that means more nitrogen from the atmospheric air is converted to NO during combustion. And we are doing a number of tricks which are highly sophisticated, and it has been a matter of research for decades, from the 80s to the very lately, to control this NOx.
Okay, so let's get into the fun stuff. So you're doing the big gas turbines and you're controlling your NOx, going to higher and higher temperatures, and then suddenly the world goes, I don't want to say climate mad, but then the priority shifts from air pollution to climate. And you've got these turbines, and let me guess, at some point around the time that you joined Hitachi, then Mitsubishi, around that time, hydrogen bursts onto the scene, and all the research efforts go into turning these turbines into hydrogen turbines. Is that right?
That's correct. I think it's a wider perspective. I would use the word decarbonize the gas turbines or the fossil power, because there are a variety of methods to do that. One obviously would be to use a carbon neutral fuel, if you have that. And for that, you need to develop or adapt the technology without making compromises on efficiency and also on the environmental performance. That means, yes, MHI was, I think, among the first, or even the first one that developed the hydrogen-fired gas turbine, and we still continue to develop that towards the 100% and so on. But we have other goodies to do the decarbonization of the fossil fleet.
Well, I was going to say, because we first met it was the Financial Times Live Hydrogen Conference, and we were on a panel, and I thought, oh no, there's going to be this chap, Emmanouil, and he's going to be banging on about hydrogen, and how it's the future. And of course, what I discovered was that, in fact, you're much more, we would say Catholic in terms of, I don't mean religiously, but in terms of, you don't mind what you do.
Although being Orthodox, right?
So I had to think twice before using the word, but that means in English usage it would just be you don't mind what you do as long as it meets the need. And so that we had an excellent conversation even back then. But I'm really interested, to what extent was the choice to sort of dive into hydrogen and taking these turbines towards hydrogen, or now doing other things, to what extent is that an internal decision, you as the technology strategist within Mitsubishi Heavy, and to what extent is it that customers ask? Do you wait until the customers ask, or do you push the technology proactively?
We always listen to the society, and this is a kind of corporate credo for Mitsubishi. So we always respond to societal needs, and this is what we are doing, and we're doing with respect to the customer. So that's a bad translation of a Japanese credo, which is 140 years old, by the way. But in the specific case of decarbonizing the fleet, this is a continuation of a long path, because even the use of gas by itself was the low-hanging fruit of decarbonization, as we have discussed last time, because of the high efficiency and the specific carbon footprint of the combined cycle. So we have achieved already in the previous decade a considerable reduction of CO2 emissions. So to achieve the complete decarbonization of the fleet, you can do two things. Either you take the CO2 out of the flue gas, or you burn zero carbon fuels. And we could not choose, in fact, and we have developed both. And this is not because we have done two mutually exclusive things, is because there are applications where you can opt for a zero carbon fuel, rather difficult and expensive ones. I already agree with you in advance. And there are other applications that we need to have an end-of-pipe technology. And these two have been adopted since 2019 in MHI, because MHI has taken the commitment to become a carbon neutral company already years ago, and we are consistent into that. We are doing Scope 1, Scope 2, and Scope 3 emissions reduction by 50% up to 2030, and we are going to be carbon neutral by 2040. So to achieve that, we need all sorts of goodies, not just hydrogen. And I think that we will have the opportunity to explain what comes to what use.
Let's come back to the targets and the 2040 and what that would mean, and also to the carbon capture. I want to just push on on the sort of, in a sense, the main turbine business, and then decarbonising the fuel part of it, because Japan, you talked about the Japanese tradition, 140-year Japanese tradition. They also have a tradition of talking about ammonia, which may also, maybe for the next 140 years, they'll be talking about that, but who knows? Maybe you'll be able to deliver it sooner. What have you got in terms of technological progress towards ammonia combustion? Because that's quite interesting, isn't it?
Yeah, that complements, in fact, the previous discussion on the emissions of nitrogen oxides, because ammonia by itself has more nitrogen in the fuel itself. So you have not only the so-called fuelenoics, the fuel coming, the nitrogen oxide coming from the fuel conversion, on top of the thermal enoics, which we discussed about. So per definition...
I'm going to do my schoolboy chemistry.
Yeah.
So ammonia is NH3, so it's 3 hydrogen molecules, or hydrogen atoms,
one atom,
which is what you want to burn, but it comes with N, so you've got a nitrogen problem.
So in weight terms, you have 14 out 17 of 17 grams of nitrogen, and inevitably some of that, when combusted, forms nitrogen oxide. So the difficulty that you very correctly touch upon earlier on the high temperature, which is a gas turbine business in combustion terms, it's augmented when you burn ammonia, and that's a really difficult challenge. And in fact, only very recently we managed to master our combustion technology to make real progress into that. Until very recently, lots of my colleagues in my métier, in my scientific cycles, they wouldn't believe that we can burn ammonia in a gas turbine without cracking it or doing something.
Right, so there's a lot of activity, or at least there's been a lot of noise around when you say cracking ammonia, that means perhaps importing ammonia into Europe from Namibia, Canada, all these things that aren't going to happen, by the way, which is a separate sort of problem with ammonia, but then extracting hydrogen from the ammonia and then burning or fuel selling the pure hydrogen.
Yeah, that's the point. And in fact, ammonia comes into picture only if we are thinking on zero carbon fuels in terms of commodity. That means production of hydrogen somewhere else and consumption somewhere else. And to bridge the distance, which is several thousand kilometers, you need a carrier, and ammonia is an energy carrier. And the explanation about Japan is that Japan has a long-standing tradition of being an energy importer, and that means that they are very keen to investigate importing decarbonized fuels at the first place. So historically, that explains the affinity that Japan had in favor of ammonia, because they thought that this is a zero carbon energy carrier. And what will be the best? Then use it as is without paying the additional energy penalty to crack ammonia, which brings another couple of steps down your ladder, and correctly so.
So yes, there's no question that being able to burn ammonia rather than having to do the extra step with all of the capital equipment and the maintenance and so on, that's clearly going to help. But a few years ago, I was in Japan. I was invited to talk about hydrogen because the Japanese plan at the time, and pretty much still today, was for transport to go to hydrogen fuel cells, for heating to go to synthetic methane, and for power generation to go to ammonia. And it felt when I went there like nobody had actually calculated the economics of that. It was just a kind of almost an article of faith that that was the future. But the economics were absolutely horrendous. And it didn't seem like that was in the public.
Maybe because Japan is used to have expensive energy. That's something that we have to bear in mind. As I told you, there are energy importers, but the mixture, there are a number of explanations, for instance, for the use of ammonia power. And for instance, in the post-Fukushima era, where the nuclear has to be shut down, Japan was forced to build new coal plants in order to sustain the energy security of the country. And that means that if you wish to bring down the carbon footprint of a coal plant, you try to decarbonize the fuel. And so bringing ammonia, and we are talking about green ammonia, carbon-free ammonia, as a drop-in fuel in a coal plant is, I would say, a sustainable way to reduce the CO2 emission.
But not economically. I mean,
it comes at a premium, no doubt about that, and that has been proven because the amount of ammonia that has been imported very recently in Japan was much lower than anticipated because of the price.
Well, so I did this very simple calculation. I said, well, if you look at if it's green ammonia, you start with green power, and then you have to make hydrogen, and then you have to do the Haber-Bosch to make ammonia, and then you have to liquefy it, and then you transport it, and then at the other end you have to gasify it, and in the end, the amount of then you have to use one of your wonderful turbines, but in the end, you get about 20% of the electricity back out that you put in at the front.
Yeah, the round-trip efficiency is not the best thing if we compare it with other energy storage. It's the seasonality that counts, it's the availability, and of course, we have to remember that this comes as a last mileage application. Before that, there are a number of things that have been done. First of all, green ammonia has to be utilized where it makes sense, in fertilizers above all, and maybe using it as a fuel in the shipping industry maybe. And at the end, the discussion of the round-trip efficiency back to power, as we say, it's, I don't like the word luxury, but it's the last part of the equation. And honestly, between you and me, it remains to be seen whether we will run this last mile at all, or it is necessary to run it, and when it will be necessary to run. But there are other, and I think that I like the parallelization of ammonia, carbon-free ammonia with biodiesel, for example. So there are other zero-carbon energy carriers that have to be compared with green ammonia. And if you do this type of comparison, then green ammonia is not that bad. That means it will find, it's finding already its position in the energy mix, but it's not one size fits all, not for everything.
And in the end, it's not a question of efficiency; it's a question of cost.
Absolutely.
And I suppose I did all sorts of calculations, and came out to be something like if you use coal-fired power in Japan is probably, I don't know, I'm going to guess something like $80 per megawatt hour, and the green ammonia electricity is going to be $400 or something, enormous. But I want to get on to, because one alternative in the power sector, even in Japan, would be actually to import LNG and then to export to capture the CO2 and then send the CO2 back where it comes from. Now, that's also could be Mitsubishi Heavy technology, correct?
Absolutely, and it has been practiced already. Japan is having a very ambitious national program on carbon capture, one of the most ambitious and also target focused that I know of. And there in this national program that has been launched a couple of years ago, we are checking in the real conditions all different alternatives like what you mentioned, having carbon capture. And carbon capture, as I mentioned earlier, is equally important than zero carbon fuels, not to say even more important because it deals with the so-called hard-to-abate sectors. And of course, what you say makes sense, but we have to remember that for the specific for Japan, storing the possibilities of carbon storage are, but there in the country, but rather limited. So there will be this cross-border transport of CO2, and we have also technology for that, not only for capture, but also for CO2 shipping. As I told you, Mitsubishi Heavy Industries is engineering company. We have technologies for literally everything.
Yeah, I'm assuming as I said, I think you would need to bring in the LNG and then send the CO2 back.
There was some discussion on dual use of ships, not with LNG. Maybe ammonia can be one of these easier in terms of configuration. But I'm not a shipping engineer. I will stick to my thermodynamics.
Yes, I looked at it, and then you've got different densities and you've got different temtemperatures and different.
Yeah, it's not that easy. It's easier said than done.
Looks good on a McKinsey PowerPoint.
Yeah, exactly. But you hardly convince a Greek ship owner to put monies directly into that. They will put their money in a variation of that.
But now the carbon capture and storage, it's not just about Japan, because you've got projects in the UK and in Italy.
Yeah.
And one of the things we can do, by the way, we'll put links into the show notes to some of the projects that you're doing. But you've got the cement factory in the UK, in Padeswood, and you've got Ravenna, where you're doing CCS, post-combustion capture in Italy. Yeah. How are those projects going?
You start from the very recent addition. We have just announced that we were awarded the contract for Padeswood. So Padeswood, it's a very interesting project, Liverpool area.
And the Liverpool area. So that's
Heidelberg Cement.
So it's connected to HyNet.
Exactly.
Yes.
Exactly. And it is a 800,000 tons per year project. We are very happy that we are building this facility, which is, by the way, not the biggest one. The biggest carbon capture project is Petra Nova in the US. Back in 2016, we have captured there 1.5 million tons and used that for EOR in the US.
Acronym?
Enhanced Oil Recovery in Texas.
Right, so that's using CO2 to get more CO2 out of the ground.
Exactly. But the first part, the checking and the viability of the carbon capture is a universal technology, but that's the biggest plant.
Now that, I don't know, the Petra Nova, that's also cement.
Yeah, no, it was a coal plant belonging to a utility, so it was capturing CO2 from a coal plant and then putting the CO2 in a pipeline.
So more like the Ravenna project, the post-combustion capture.
Yeah. The Ravenna was a very interesting one because although it's small in size, it has been selected and constructed as a fully industrial project by our partner there, Eni, the Italian oil and gas major. And it was linked together with the reactivation of the Ravenna carbon storage project, which is the second European carbon management infrastructure project after Northern Lights in Scandinavia. So we are very proud that these two things, the start of a second storage facility and the first capture was done with our technology.
And Northern Lights is the one over on the other side of the UK, in the
Sleipner, Norway. The three storage sites in the northern part of the North Sea.
Which I think also the UK, there's also supposed to be CO2 coming from the northeast of the UK. I'm not sure if that's still on.
Shipping that it would be an option, but the UK is developing also their own storage infrastructure, which are very important.
Right. So let's go back to Padeswood, because that's interesting. It's cement, but it is it is absorbing the CO2 from because in cement you've got two things going on. You've got process emissions. So when you make cement, the process of decalcination produces CO2. You've also got CO2 that comes out from potentially the combustion of the fuel used to provide the heat.
Absolutely.
And those are, in the case of Padeswood, they're mixed, and you are then. It's a little bit similar to post-combustion separation. It is a post-combustion separation.
It is a scrubber, and that's why the reason of selecting the amine scrubbing technology of MHI in the particular project is because it dealt with both emission sources, the inherent CO2 emission from the calcination process, and also the combustion CO2, so to speak.
And you've got these marvelous, I guess they're sort of types of amines with wonderful names and acronyms. And
yeah, that's also something that MHI is very proud of because it is a liquid solvent. And it's, I think the saying that is simply an amine, it's understatement for this type of solvent.
This is the famous, or soon to be famous because of this show, KM-CDR21.
KS21, and the process comes, it's a Kansai Mitsubishi process. Long story short, it's a very efficient, in terms of regeneration, because we have an energy penalty to regenerate the amines by releasing the CO2.
Here's my question though. If you used electricity to do the cement process, then only the process emissions would come out.
Exactly.
Would you still be able to use this marvelous
Why not?
etc.? Because you would be able to. It would
we,
still
we,
have its role.
we would. Of course, in that case, there are other. I mean, there are other technology that for the calcination itself might be applicable. Depends, for instance, if you have oxycombustion. If you have pure oxygen on site, then you produce CO2 at a very higher concentration, and that can be captured in other ways.
Because I know other people are looking at using using electricity for the heat and then a heat battery, so there's no combustion.
Yes.
So then I think what you get out is a pretty pure CO2 stream.
High concentration CO2, and you can condense condense CO2 and separate for that.
Okay. So
the heat battery is a very nice point that you mentioned. Heat battery means using electricity stored in the form of heat into some type of inert material. That is something that we have also in our technology portfolio, for instance, for the steel business. But still for the cement, the amount of energy needed on the calcination process is huge. It's an emerging technology. It's not state-of-the-art right now.
No, and I certainly, my ingoing assumption is that for cement, we're going to need to do carbon capture and storage.
We call it hard to abate.
And some people really hate CCS, carbon capture and storage, and I just say get over it because we're going to need it.
As I am in this business quite a long time, I remember same people hating the sulfurization plant when I started my career back in the late 80s. Nobody was believing that we were going to retrofit all these coal plants we had at that time with desulfurization. They all said that it will ruin the economics. What are you going to do with all this GIPS that comes out, and you are this and that? And at the end, because it's an end-of-pipe technology, and because there was a societal commitment for that, it becomes the standard state-of-the-art technology. I'm not saying it will be oversimplistic to claim that carbon capture, post-combustion capture is one-to-one to desulfurization, but for certain technologies, it definitely is, and I'm not afraid to pay the penalty or to put the price of capturing and managing the CO2 into the equation. At the end of the day, this is why we had the ETS made to benchmark ETS against the capture and handling cost.
And I've said elsewhere that...
ETS, emission trading system, sorry.
Thank you very much. You caught your own acronym there. I was saying that I have said elsewhere that I think we're going to need to do carbon capture and storage for blue hydrogen because it's going to be cheaper than green. So
Absolutely.
we better get used to doing it for that. Also for process emissions like cement. And we're going to get onto biocarbon removal because that will allow us to then emit small amounts in other sectors. Cleaning Up is proud to be supported by its leadership circle. The members are Actis, Alcazar Energy, Arup, Copenhagen Infrastructure Partners, Cygnum Capital, Davidson Kempner, Ecopragma Capital, EDP, Eurelectric, the Gilardini Foundation, KKR, Mitsubishi Heavy Industries, National Grid, Octopus Energy, Quadrature Climate Foundation, Schneider Electric, SDCL, and Wärtsilä. For more information on the Leadership Circle, please visit cleaningup.live. To keep up with all that's going on in the Cleaning Up universe, make sure you subscribe to our newsletter. Written and edited by my long-time New Energy Finance and Bloomberg NEF colleague, Angus McCrone, it comes out every second Monday. Angus provides the latest on the episodes we're recording, the events we're hosting, stories we're watching, and what Bryony Worthington and I are up to. To sign up for the Cleaning Up newsletter, visit cleaningup.live. Before we get onto the bio side of things, where I know that you've also got activity, it's one of the reasons I love Mitsubishi Heavy, because you do, I don't want to say a bit of everything, but you do quite a lot of everything. And you mentioned steel.
Yes.
And that's another area where you've got very substantial activities and also low carbon steel activities.
Yes, that's correct. Mitsubishi Heavy Industries has a subsidiary which is called Prime Metals. It's one of the leading engineering companies on the steel making business, both upstream and downstream. That means both in the furnace and the production of iron, and also in forming steel products and so on. And in that context, we have been very active in what we call green steel. That means reducing the carbon footprint during the steel production. By the way, you know that steel production is one of the biggest emitter of CO2. And not only by using scrubbers like the carbon capture, but also by decarbonizing or moving to more and more into electric arc furnaces. That means electrification, a topic that I know you like very much. And also using hydrogen reduction for the reduction of iron oxide by what we call direct reduction process. So there is a portfolio of technologies, and we see demand on green steel picking up because of different, branding and quotas and public procurement issues, and also as a characteristic of European made in Europe production, and green steel and made in Europe can go well together hand in hand. So that is also a point of activities of MHI.
So a couple of years ago, certainly 3 years ago, it was all about green steel was going to be, zero carbon. It was going to be hydrogen. Of course, there's a big project up in Sweden, Stegra. I don't know exactly where they are today, but not perhaps, we're not quite sure economically, not quite sure if they're going to get there. But very much the trend has been towards saying, well, we'll go to DRI. Of course, we'll do the electrification, right? If you have electric arc furnace, but that's really for recycled steel. Yes. It doesn't solve the primary steel problem. DRI, direct reduction, does solve that. But there seems to have been quite a retreat from hydrogen direct reduction and towards just going with natural gas. And you get most of the climate, most of the emissions reduction benefit. So have you, Mitsubishi Heavy, also, have your customers and you, therefore, decided not to go all the way to hydrogen and pure hydrogen and fully green steel?
It's always the same discussion about hydrogen. We have the technologies for the hydrogen use, but we don't have the hydrogen. So it's a question of availability of hydrogen. And in most cases, and this is a nice thing on the DRI, that you can start with natural gas. In fact, that goes very well together with CCS. And you need anyway a bit of carbon for the reduction purposes anyway. And you can gradually substitute if and whenever natural gas with hydrogen without changing anything else in the technology itself. So it's not going a gas. Simply speaking, a gas-driven DRI plant will never become a stranded asset, even if you have abundant hydrogen available around there. So that's the main driver, and we see customers and partners all around the globe following this path.
And so the approaches in those projects that you've got, they are, in a sense, forward compatible. So you can start with 100% natural gas, but you could
gradually switch.
And you could gradually switch. And is that your own steel technology? Because you work with partners. Everything is with partners in these huge projects.
Yeah.
Who's doing what in those steel projects?
The steel technology, the furnace or whatever, it's prime metals. In the DRI itself, we have a license from Midrex. The original technology comes from Midrex, but this is a prime metals technology. Prime metals is the licensee of Midrex.
Because one of the things that I was reading in preparation is that it's flexible to different ore qualities. Because what I had heard is that this DRI, directly reduced iron, one of the problems, and the problem in Sweden, is that it can't use lower quality ores. So are your partners or your technology is different?
Yes, and not only that, but we have a very big R&D, research and development product. Prime Metals is having this program on producing different, we call it high-4, that means producing different parts of different types of iron ore or the particulates which are better suitable, for instance, with smaller size and things like that benefit with DRI. Long story short, there are technology developments not only around the DRI, but also around the preparation of the material and so on. And because now the university professor speaks and the researcher, you have to remember, and I'm giving that as a topic for the next ladder, the use of metal oxides. You mentioned the Carnot battery, the high temperature battery. Think of the metal...
The heat battery. Yes, sorry.
So I'm calling it Carnot, it's the same thing. Yeah. Think of the metal oxides and the rapid oxidation as a power cycle, and then think on the metal oxide reduction as charging a huge metal battery. What I'm going to say is that in the future, maybe in the next decades, there will be other alternatives on zero power and metal oxide power cycles, which is now a very low, it's still on the R&D and very low technology readiness level, that might combine together with a reduction process and form a closed loop which has zero carbon power production on the one side and renewable electricity storage in the form of the ore on the reduction side.
Well, so there is, of course, a company called Form Energy, which is doing the iron batteries, iron air batteries, and they've just signed a big deal with Google.
Yes.
We did an episode, I spoke to Matteo Jaramillo, who's the CEO.
Oh, I didn't know about that. But I am personally very much interested in this oxide cycle. Is it alumina or iron?
It's iron, and I have to be completely honest that I'm not a big believer in the economics of that, because 100 hours to charge and 100 hours to discharge very much reduces the number of cycles per year, and it means you can't charge quickly when there's a rapid drop in the power price and be ready for a long discharge.
Obviously, that's a long duration charging. It's another animal, so to speak. But metal battery, maybe it's not the best cycle, but that is something that I feel that it may bring something different in the future.
So I am very interested in the electrolytic process for iron winning. So there's Boston Metals, Fortescue's got a process and so on.
Yes.
But the general point, I think, behind this is that isn't R&D wonderful? And what problems yield to it? There's, I think...
safety issues on the power cycle also. You know, you have the explosion, the fire protections, scaling up. The knowledge that we have in this rapid oxidation is very minimal.
But I'm thinking even more generally than that. If you look at, when I'm told, you can't make glass using just electricity, you have to use a gas, or bricks, you can't fire bricks because they don't end up looking right, and so on. And I just look at it and say, how many researchers, how many engineers, some problems, okay, if you've got a fundamental sort of second law of thermodynamics or Carnot efficiency problem or irreversibility problem, you're not going to be able to solve that, but so much will yield to research over the next decade, 2 decades.
I think that's a valid point, and I'm a great believer of electrification. That was maybe your surprise the first time we have met, but I do believe in electrification. That means lots of these are coming together with electrification. And of course, electrification has to be pursued in a variety of ways. Electrification calls also not only on the different processes, different consumers' behavior, different, active consumers, demand-side response. There are a number of things that could be achieved with electrification, no doubt about that.
And another of your businesses that I want to make sure gets a mention, because I love them, heat pumps. Is it the biggest heat pump in the world?
Yeah. That's the Turbines heat pump that we have inaugurated very recently and make the news. It's a fairly big heat pump and producing steam. And it's the core. It has also Mitsubishi technology because the compressor there, it's a Mitsubishi compressor running in this isobutane and things like that.
And that's 12 megawatts, and it's in Finland, which means I guess it's in the wood pulp industry.
Yes, that's correct. And I haven't visited myself after they put it in operation, but I have subscribed. We have now. It's so popular that we have a priority listing, and we have 6 slots. I think I was told, so that we can try to go with elbows. Who is going to see? So it's a fantastic business, the heat pump business, and it's. It's one of the things that there will be lots of improvements in the future. There will be improvements not only on the use cases. Nobody would have thought that we will produce steam from a heat pump some 10 years ago. It will be the use cases. It will be... I'm not speaking, to make myself clear, we are not so much in speaking about domestic heat pumps. That is another product. We have it in our portfolio, others have as well, but I'm speaking here on industrial scale heat pump.
So I have a Mitsubishi heat pump, but is that one of yours?
It's maybe it is Mitsubishi Electric, one of the Mitsubishi cousins or something.
It is Mitsubishi Electric.
Somehow.
But the one you're talking about in Finland, just to be clear, that's 12 megawatts.
Yeah.
It's producing steam at, I think it's 4 bar. It's 180 degrees centigrade. Yes. It's got a coefficient of performance of 2.2 or 2.4. Fantastic.
Yeah, and the challenge, and this is about economics. I mean, remember that in the domestic sector, COP, coefficient of performances of 2 is considered very low. In the industry sector, because you are competing with a gas boiler to do the job, COP of 2 is fantastic.
Right, and you're taking the waste heat from the plant and then recycling. Exactly. So it's kind of the circular economy
at its best.
Inside a factory. The company that did that big project in Finland is Turbines, so it's a subsidiary of yours, also very active in geothermal. I've come across it because they are involved in the Geretsried project of Ever, whose former CEO has also been on the show.
Oh, that's I didn't know about that, but I know Geretsried project quite well. It's in Germany, and of course, Turboden originally comes from the organic ranking cycle, which goes hand in hand in geothermal applications. We are very happy that we are traditionally geothermal has been a field for MHI. Japan, geothermal energy. If you travel to Iceland, you will see geothermal plants of MHI producing next to Blue Lagoon, for example. But in the case of Turboden, we deliver big organic ranking cycle facilities for geothermal applications, like we are doing Fervor in Utah, in the US, fairly big plant, 300 megawatt. Geretsried, you mentioned, and there are more plants coming out. And this is a very happy coincidence because geothermal is one of the favorable energy generation techniques which deliver 0.24 with no carbon footprint. So that's another sign of the broad range of products that MHI is bringing in the decarbonization business.
You know, we started off talking about 1,700 degrees centigrade and Turboden with the organic Rankine cycle.
35.
Well, operating at not quite 35, but no, it's not, well, the intake temperature would be 200, yes, 300, but not more than that.
The working medium, I was referring to the working medium, which can be very, very low. ORC, it's a very interesting technology, and it's one of the examples I'm using to my students, which is a technology that has a very poor thermodynamic efficiency because opposite to the gas turbines, it goes down in the Carnot ladder, but because it exploits zero cost waste heat, it's highly efficient, highly economic, and very important in terms of balancing services in a decarbonized grid.
Everybody is going data center crazy, and you also have a data center proposition. What is it?
Yes, the data center for us, it's one of the signs of the technology company that we are. Our ambition is to offer one-stop shop solution for the data center. So we have this, we launched also even a containerized data center application in a 20-feet container, which we call Dia Vault, which is a small scale, very small scale data center, fully integrated. And in this data center supply, we have lots of bits and pieces of interesting technology. Obviously, even in the bigger, with the big size data centers, we are taking care of the energy supply, obviously, not only with gas turbines, with gensets, with batteries, with whatever, but we are doing the cooling, and we are doing both refrigeration and energy recovery from refrigeration, but we are offering also direct cooling to the chips with the proprietary technology that we have. So we are offering different bits and pieces so that the hyperscaler will not go shopping in the supermarket of technologies and trying to put everything together. They just shop in the Mitsubishi stand and get the full solution.
In the company store.
Exactly.
You recently acquired a company called Concentric in that space. What does Concentric do?
Yeah, that's about energy management, because the glue around this data center business is the energy management, and Concentric is a company in the US who was specialized in doing energy management in data centers and things like that. So we have both the hardware and I would say the software to manage the whole thing.
Okay, so from the EPC, the engineering,
procurement and construction.
So you do that, but you also then have various of the components.
We prefer, in general terms, we prefer the EP of the equation, and we leave the construction obviously to more competent partners which are on the ground.
The more E, the better, the more energy.
The more E, of course, for engineering, but procurement is also nice if you think on the financial returns.
Now, in the interest of time, you've got a nuclear business, but it's not kind of it's the balance of plant, we'd call it. It's the stuff around the nuclear reactor, not the nuclear itself.
There is a nuclear business. I'm not a nuclear guy myself, but I'm very proud that Mitsubishi has contributed to ITER, for example, to the nuclear facility of the EU in Kakaras.
The fusion, fusion.
So
reactor.
the pressure parts of that.
Yeah.
And of course, nuclear is a very important part in our business. We are doing all the pressure parts for nuclear reactors. We have, and I don't think that even if I'm allowed to say that I'm a big supporter of nuclear energy, although professionally, in my professional career, I never had anything to do, except that the possibility that we can use nuclear energy to create the so-called pink hydrogen, if you remember our chat last time.
I think expensiver and expensiver perhaps would come to mind. But I mean, look,
gas-cooled reactors in the future could deliver hydrogen as a byproduct, but that is in the future.
At the cost of then not making electricity, which is of course more exergy, higher value, etc. I have a small amount of nuclear engineering background, so you won't find anybody, at least in this room, upset about the fact that there's. But nuclear, it is having a resurgence, there's no question, and it's got turbo generators, it's got heat management, it's got heat loss or heat that needs to be either recovered and used, and so clearly a fertile area for the sorts of skills you've got. But I want to go full circle in your career and get back to power to X.
Okay.
You were not going to get away without talking power to X. Okay, so you've got activities in that space. I think you and I have already agreed that the hydrogen economy is really probably not going to happen, or that it's not going to happen. But parts of it could happen. Which parts do you think are likely to be viable?
Yeah, the ones that combine hydrogen as a storage, that means the precondition for everything is that you have abundant renewable electricity and you can have some competitive hydrogen. The ones that combine, for instance, biogenic CO2 with hydrogen, and I think in that context, synthetic fuels in whatever form, methanol to start with, which is the simplest molecule, but also the whole discussion about synthetic fuels, especially when you use biogenic CO2, they will have their place in the mixture. And methanol, you mentioned about methanol. I have done the first power to methanol project within MHI. We have done it. We have a facility in RWEs, in the German utilities plant in Niederaußen. I have started that already back in 2015, 2016. So we know the economics, we know the technology. We have also new technologies that are facilitating this co-processing of CO2 with hydrogen. I am very proud being a member of Mitsubishi family because Mitsubishi launched these solid oxide electrolyzers, and we made an announcement that we have done, for example, co-electrolysis of CO2 and steam, which could render a mixture of CO and hydrogen, which already is a precursor of whatever synthetic fuel business. So there will be applications, and in the future I think co-electrolysis is a very promising technology. But before that we have to agree on the basics of the methanol, maybe, on having methanol as a building block either for chemicals or the usual, I mentioned that already, the comparison to biodiesel. I always, the way I have convinced myself on doing Power to X is by comparing, and that's in a very interesting ladder that I would suggest to you, the CO2 avoidance cost ladder. And in that ladder, the biodiesel is very, very expensive in terms of the CO2 avoidance cost. So alternatives to biodiesel or biofuels deserve a place in the market, and synthetic methanol is one of them.
So it's quite funny because I get quite a few requests to do different ladders and so on. I did the hydrogen ladder. I've done the electrification staircase. And one of the upcoming episodes, I'm going to go over to Brussels and talk to a number of people and kind of launch it or relaunch, or not relaunch, but really try to publicize it. But there's also CCS ladders people want, biocarbon or biogenic carbon ladders and so on. What you'll notice is that in the most recent version of the hydrogen ladder, which is still version 5 from, I think, 2023 or 2024, it's quite long in the tooth. Actually, aviation fuel is fairly high up, but not hydrogen in aviation, but it was biogenic carbon with hydrogen.
Absolutely.
And Rob Miller, I went and visited the Whittle lab in Cambridge, and he persuaded me that that might be a thing. I actually now think it probably won't be a huge thing because carbon removal looks like it would be cheaper than that kind of, even that, he called it PBTL, power and bio to liquids, or power to X, but using biogenic carbon.
Yes, that's correct. I think there will be a number of usages of biogenic carbon, and it's, we are in the so-called biomass energy CCS, the BECCS. If you have scale, if you want to produce the hundreds of thousands of tons of bio CO2, you can't do it only by means of carbon capture of biogenic combustion, which is a very interesting alternative, for instance, if you look to waste-to-energy plants. If you wish to decarbonize waste-to-energy plants, this type of CCS and, discussing about the biogenic CO2 is an interesting. And of course, carbon removals there play a role because at the end of the day, it's about the finances and the equivalent pricing that CDR is paying opposite to ETS, especially nowadays where ETS is not in the best form in Europe.
So CDR, carbon dioxide removal, ETS, Europe, the European trading system, the emission trading scheme. And yes, I think that's really interesting. And it was certainly in the piece that I wrote last year called The Pragmatic Climate Reset, one of the things that I was saying is that we really need to go back to value for money tests. And the value for money in this space is, in terms of the climate solutions, has got to be dollars per ton of CO2 avoided or absorbed or removed or whatever. And you're right, biodiesel kind of, very expensive compared to some of the other things we can do, because we've kind of chosen our solutions by their political acceptability. Doing e-jet fuels at 12 times the cost of kerosene is not going to be a thing. But it's
keeping the farmers happy is also an important part of the equation.
It is, but the problem is when the numbers get so big, you don't have enough money to keep the farmers happy, and that's where. But what I like in terms of power to X, I will be honest, if there was another version of the hydrogen ladder, I like what Henrik Stiesdal, another former guest on the show, is doing, and that is in Denmark, where there are already biodigesters, which Denmark is full of biodigesters, and they produce CO2, which, little known and dirty fact, is it's mainly just vented to the air. But you could actually use enzymes or bacteria to combine that CO2 with electrolytic hydrogen and increase your yield. It's kind of yield enhancement.
Absolutely, and I'm confident that this will take its place, especially this bacterial way of treating, which at the end of the day is mimicking nature, and mimicking nature is always a good thing.
Well, yes, except that it's mimicking nature using bacteria from the Mariana Trench, not actually bacteria that you would ever find
outside of Copenhagen.
Not exactly Danish bacteria. But I must say, I do think you're right that power to X, there could be applications that are kind of cheaper than some of the other stuff we're doing.
Yes.
And that might be enhancing biomethane yields. It might be in methanol. I actually have always held a bit of a candle for methanol. I quite like methanol.
Yes, everybody likes methanol because of the simplicity, which is the first step It's always the basic chemical, as we say. But I need to remind you what we were talking in the different processes. When you produce synthetic methanol, you have to be careful what you wish for, because you get it with 90% water in some cases, and that's not exactly the fuel we are opting at. But definitely methanol as a basis fuel, or other solutions, synthetic gas. There are these two competing paths towards synthetic fuel. And honestly speaking, I don't know which one will win. There is the methanol path, and there is the Fischer-Tropsch, the more traditional synthetic gas path. But yes, I don't know which one is going to win.
You talked about the co-electrolysis. Yes. So that is taking CO2, probably, well, I would like to think biogenic CO2 rather than just from combustion.
Biogenic CO2.
And then using electrolysis, co-electrolyzing it with steam, and it produces
CO and hydrogen. So you have the first step, you have syngas.
Syngas.
So you can do syngas is a very nice thing, and that's why historically it was been the fuel of preference even in the times of scarcity of raw materials. I'm not saying that nowadays with the crisis of in the Gulf countries we have to go back to syngas and. But it's a very interesting path, this CO-hydrogen mixture, very well known.
But can I ask you this? Okay, so syngas, which is essentially town gas, I mean, this is what we used to use
in the past.
Yes. And of course, you can then Fischer-Tropsch it and make a diesel, make kerosene, make whatever, right? But can you not just store it and then use it in one of your fabulous turbines? And why wouldn't you do that?
Of course we do it. Of course we're doing that for decades, but we don't make publicity. All our industrial gas turbine, and that's why we were so good placed to adapt the hydrogen and the alternative fuels. Our industrial gas turbines, which are using different off gases from industrial processes,
naphtha, and
from the steel industry. We are doing that since 30 years or something. Once again, we are very proud of our gas turbines. I need to say that once again.
So what I'm taking away from this last bit of our conversation is I need to do another deep dive into the biogenic carbon, how best it's going to be used. I know I flagged that as something I need to dive into more. I probably need to update the hydrogen ladder one last time, but everybody will hate what I say anyway on that one. And also syngas or synth gas. I want to understand it a little bit better and how we might use it.
Yes, because you mentioned already synthetic methane, for example, SNG, and not synthetic natural gas. So that means synthetic. All these components are in competition within each other, and at the end, whenever you have competing solutions, something is gonna win. And maybe, why not, syngas, which has been around for how many years now? More than a century. Much more than a century. Maybe has also a position in the carbon-free, provided, and that we have to be very knowledgeable and remember that, provided that we keep our appetite for decarbonization. That's a driver that is not, I would say, negotiable, or you cannot make, discounts.
Yeah, I think that's a salutary point, because if you look at electrification, there's a whole load of stuff where it can actually be cheaper than the fuel-based alternatives.
Absolutely.
But a lot of what we've been talking about, it is going to have a carbon price. It could be higher, it could be lower, but if the carbon price is zero, there's a lot of stuff we won't do. It's enormously fun for me to talk to you. It's enormously interesting. I am an engineer who never worked as an engineer, who's doing this instead. I can't wait, Emmanouil, to get you together with some of our other leadership circle members, people Schneider Electric and Arup on the building and energy system side of things. Wärtsilä, you've got you cooperate with Wärtsilä on all sorts of,
of course.
Shipping marine type projects. I really look forward to working with you.
Yes, Thank you. Thank you for having me. It has been a tremendous pleasure to exchange arguments with you, and I look forward to our next meeting.
So that was Emmanouil Kakaras, until recently Executive Vice President for the Green Transition at Mitsubishi Heavy Industries, now their Technology Evangelist, and also Professor of Mechanical Engineering at the Technical University of Athens. As always, we'll put links in the show notes to resources that we mentioned during our conversation. Too many to list here. Go to the show notes and you'll find them. And with that, let me thank our producer, Oscar Boyd, our video editor, Jamie Oliver, head of operations, Kendall Smith, the team behind Cleaning Up, the Leadership Circle, without whom none of this would happen, and of course, you, the audience, for joining us, spending time with us here today. Please join us this time next week for another episode of Cleaning Up. Cleaning Up is proud to be supported by its Leadership Circle. The members are Actis, Alcazar Energy, Arup, Copenhagen Infrastructure Partners, Cygnum Capital, Davidson Kempner, Ecopragma Capital, EDP, Eurelectric, the Gilardini Foundation, KKR, Mitsubishi Heavy Industries, National Grid, Octopus Energy, Quadrature Climate Foundation, Schneider Electric, SDCL, and Wärtsilä. For more information on the Leadership Circle, please visit cleaningup.live. If you're enjoying this episode, please hit like, leave a comment, and also recommend it to friends, family, colleagues, and absolutely everyone. To browse our archive of around 250 past episodes and to subscribe to our free newsletter, visit cleaningup.live.